So far in this series, when we've spoken about gases, we've generally done so in the context of a single molecular or a monatomic substance. But the truth is, the gases we encounter in the real world are almost always mixtures. The air in Earth's atmosphere, for example, contains nitrogen, oxygen, argon, carbon dioxide, water vapor, and several other trace gases. So it's important to understand how mixtures of gases behave and how to quantify their composition. When dealing with gases, one of the easiest measurements to make is to assess the pressure of a gas. So let's start there. These two cylinders have the same amount of gas in the same volume at the same temperature. The type of gas is different, but kinetic molecular theory says that if all those conditions are equivalent, the pressure should also be the same. Remember that this is because kinetic molecular theory assumes that the shapes, sizes, and intermolecular forces of gas molecules are negligible when it comes to modeling their behavior. The only difference left is that the nitrogen molecules are heavier, but they're also moving more slowly, so they'll be expected to exert the same amount of total force on the walls of their container as the lighter water molecules in the other tank. Hopefully we can imagine what would happen to the pressure then if we put both gases into a single tank of the same size. You'd expect to have twice the pressure, right? And if you added the same amount again of a third gas to that cylinder, you'd expect the pressure to be 3 times higher. This is true, and it illustrates the principle that we call Dalton's Law of partial pressures. The total pressure of a mixture of ideal gases is equal to a simple linear combination of the pressures that each gas would have on its own. When they're all part of a mixture, those individual contributions from different gases are called partial pressures, hence the name of the principle. We can go just a bit further with this idea. One more thing that you may have noticed in these examples so far is that the amount of gas in each cylinder is going to be directly proportional to the amount of pressure that it contributes when they're mixed. This relationship didn't get called out in our previous video on gas laws, but we can see that it derives straight from the ideal gas law just like the others. What this means is that if you know the relative abundance of one of your gases in a mixture, and you measure the total pressure of the mixture, you can calculate the partial pressure of that gas directly. In practice, we call that relative abundance number a mole fraction. It's often represented by the Greek letter chi, and it's just a ratio of the moles of your designated gas over the total moles of gas in the mixture. Let's try this out by returning to the air example given at the beginning of the video. The composition of air at sea level is such that if you had 100 moles of air, about 78 of those moles would be nitrogen gas, about 21 of those moles would be oxygen gas, and about 1 of those moles would be argon. Because our total sample here was 100 moles of gas, it should be easy to calculate mole fractions. We just take each amount over the total to get a decimal value. Then, if we wanted to calculate the partial pressures of each of the component gases, we could simply measure the current atmospheric pressure and multiply it by each mole fraction. The barometric pressure when I recorded this was 75.1 centimeters of mercury. Let's do some quick dimensional analysis here with our pressure units to convert this to atmospheres. As expected, we get a value of right around 1 atmosphere. Carrying out the appropriate multiplication, we end up with the partial pressures contributed by each major component of our air mixture. Partial pressures become very important to consider, especially when handling and performing reactions with gaseous reagents. We'll take a look at some specific applications in a future video. Thanks for watching.